Moving on, let's calculate moment of inertia using integration. So to do this, this is where we have a function and we set some axes, our x and y axis. So this would be some function of x, and we want to find the moment of inertia of this shape here. This is good when we have more abstract shapes, some kind of odd thing that we're making, not a basic square, not a basic triangle, something that's some weird function, or it might be made up of multiple functions that you can find the moments of inertia for all of them. Okay, but what we want to do is define a rectangular differential element. So instead of having a differential area, which is a little square one, because that has to be integrated with respect to x and y, we're going to try to make a rectangular element that's either dx wide by y tall, or one that is xy by dy tall. So the dx wide by y tall is going to be a vertical element, and then the x wide by dy tall is going to be a horizontal element. Okay, and then you can, for a vertical element, the one that's dx wide, that one will just, dA becomes y times dx. So then we're just integrating with respect to x, and if we've got a horizontal element, we're integrating with respect to y. Now, why would we pick a vertical or a horizontal element? There's several reasons. Pros and cons. It's not always an easy which one's the right answer. There's things that you can weigh. A few of the reasons. If you're looking for I sub x, it might be easier to choose a horizontal element. And if you're looking for I sub y, it might be easier to choose a vertical element. Now, if you're looking for both, there's two separate calculations. You can use the horizontal element for I sub x and then the vertical element for I sub y for the same function. Now, I say it might be easier. This isn't a huge deal breaker. Mainly the reason that this one is in here is that keep in mind that if you have a vertical element, you're finding I sub x, that vertical element has its own moment of inertia about its own centroid. So you have to deal with the parallel axis theorem. It's actually very easy to do. So this is actually kind of a minor consideration, but it is a consideration. This one's a bit more important, at least in my book. If the function is solved in terms of y and not easily rearranged, then you're going to want to integrate it with respect to x, right? If you cannot get it to be x equals, and then y squared plus 3y plus 12, it ends up being the difference of y minus 3, the quantity to the third power, or worse yet, like to a square root of a difference involving variables. That, it can get tricky to integrate, and you have to use U substitution or some technique of integration. It can all be done. It's not the end of the world. But again, a lot of times you can get a simpler integral by picking one or the other. So a lot of times we have equations solved for y. So y equals mx plus b or whatever. And if that's the case, then I'm usually going with a vertical element because it's already got a dx, it's already solved in terms of x, so I can just stick dx on the end, make my vertical element and integrate. It's usually a bit easier to carry out the integration.